Finally, we'll discuss here the shear stress due to bending. For this one, again, I will take the example of a circular bar and we'll fix up our coordinate system at the centroid of the cross section, and along the length of the bar, we'll fix up our z-axis. And let here the vertical force will act at the free end, and let the other end is fixed end. So we'll consider here one cross section at the fixed end, and we'll show the reaction of the force. Due to this force, there is a bending is taking place above the x-axis. Now let's consider here that this section is the at point A, which is at the fixed end. So I have to slightly show here thickness, and we are interested on this area. What will be the stress acting due to the force F? So when this force is acting at the free end, then we have to do the balance. So if this one is the force F, the same force you have to show here also. So this one is a balance, and because of this one is the action. So one reaction force will act on this area, that will be equal to F. This force will be taken as a shear force equal to V. Plus we have additional bending moment will also takes place, but this time we are only interested in the shear force. So this time the area A, which one is the circular cross section, and the force F are parallel to each other. So we have pi by 4 into d square. In this case, we have to calculate here the shear stress. That will be the shear stress due to bending. This value of the shear stress in general is given as tau is equal to the shear force multiplied by area into y bar. I will explain this, what is area and y bar, divided by the moment of inertia, that is the second moment of inertia, multiplied by thickness. Already we have introduced the neutral axis here. So for this area we are developing the figure. This one is our neutral axis, and we are interested to know the shear stress at a certain distance y from the neutral axis. So let's say here at this fiber we are interested to know what is the shear stress. So this distance will be taken as equal to y. In that case, you have to calculate the area of this figure. So whatever the area of this figure will be equal to A. Then you have to find out the centroid of this area, that equal to C, and you have to measure the distance equal to y bar. And what is the thickness at this section? That is, this one is thickness, that equal to T. In this fashion we can calculate the shear stress due to bending. I represent here the moment of inertia for entire section. So this time we have I is same as equal to pi by 64 d to the power 4. Naturally here this area will be more if we have y value is equal to 0. So whenever we have a circular cross section, then at neutral axis we'll find here the area is maximum, and because of this we have maximum shear stress is produced, that will be equal to tau max. If you add the top fiber and the bottom fiber, then the area will be equal to 0. So at this point here the shear stress will be 0. At this point here the shear stress equal to 0. We can say at y is equal to d by 2, and at y is equal to minus d by 2, the shear stress is 0. And then we have a distribution here is in the parabolic form. So this one is the distribution in the case of shear stress due to bending. This value of tau max in the case of, so when you consider tau max, then you have to take the area equal to above the neutral axis, and tau max in this case will be given as 4 by 3 multiplied by the shear force V divided by the entire cross section. This value is called as tau average. So we have tau max is equal to 4 by 3 multiplied by tau average. And if you have a rectangular cross section, so this one is a rectangular cross section of width is equal to B, depth is equal to D. In that case we have overall area will be B multiplied by D. So this one is again a neutral axis here, and neutral axis that area will be maximum. So again we will get the maximum value of the shear stress at the neutral axis. At this point here there is no area, so shear stress will be equal to 0. Again we get a distribution here somewhat parabolic, and we have tau max this time will be equal to 3 by 2 of tau average. And how are we going to calculate tau average? So for tau average, you have to simply divide the shear force by area A. So these are the distribution of a shear stress due to bending. This one is also a shear stress due to bending, but for circular section. In circular section, the maximum shear stress is 4 by 3, and in rectangular section, it's a 3 by 2. And this is the basic definition how to calculate the area and y bar in the calculation of shear stress. I is remain constant, V is remain constant, T is variable, that is the thickness will be variable, and the area and y bar is variable. As far as the moment of inertia of the rectangular section is considered, it's a BD cube by 12. So when machine component is subjected to only axial load or only bending moment or torque, the uniaxial state of stress is produced that we have discussed up till now. But in actual practice, the components are mostly subjected to combination of loads. Example, if the transmission of a shaft is subjected to bending and torsion at the same time, combined loading leads to a complex state of stress. Infinite number of stress vectors at any point inside the member subjected to combined loads, as infinite number of planes can pass through the point. Each stress vector is characterized by surrounding plane on which it is acting. And the state of stress at a point is totality of all the stress vectors acting on it. So for design purpose, I will consider here one L-shaped rod which is fixed at the wall, and the length protruded from the plane is equal to L, and the perpendicular length is equal to A. At the free end, we are applying the force equal to F. We want to analyze at the fixed end what is the state of a stress and which one is critical section. So here objective is to analyze the state of a stress at the end of the rod. That is the fixed end we want to analyze. So this force you have to first shift to the fixed end. Let's say this point equal to O. So at this point the force is shifted, then the force will be acting as it is without change in magnitude and direction. Second case, to obtain the effect of this force about the fixed point O, you have to take the cross product of position vector of point P where the load is applied. Using the cross product of R bar and F bar, we can find out the moment about the x-axis, y-axis, z-axis. So when you take a cross product of R bar, that is the position vector of point P with respect to F bar, then this will generate a cross product. Cross product will be mxi plus myj plus mzk. But for this one, we have to set our coordinate system. So you have to set our coordinate system at point O where we are interested the state of a stress. This axis we take as a standard axis equal to x. Vertical axis will take as equal to y. And how much portion it protrude, that will be our z axis. And once you take the cross product, then you get a value of mxi plus m by j plus mzk. In that case, the value of mx will be the bending moment about the x-axis, and clockwise moment will be taken as negative, anti-clockwise will be taken as positive using the standard right hand rule. My is equal to bending moment about the y-axis. Again, we have a same sign convention, that is we have clockwise. Bending moment will be taken as negative and anti-clockwise will be taken as positive. And the bending moment about the z-axis will be taken as a torque, that is a twisting moment. So first of all, you have to find out the position of point P with respect to origin. So this one is origin. So how much distance you travel along the z-axis? So along the z-axis you travel the distance equal to L. Then this distance is traveled is parallel to x-axis. So along x-axis you travel a distance equal to A. But along the y-axis you did not travel any distance, so y value will equal to 0. So coordinate of point P is given as x, y, z will be equal to, x coordinate will be same as equal to A, y coordinate will be 0 and the z coordinate will be equal to L. Since we are interested to find out the position of point P with respect to O, so our position vector R bar P is simply equal to the P minus O, that is a 0, 0, 0. So we have P is A, comma 0, comma L minus origin is 0, 0, 0. So in this case, position vector will be AI plus 0j plus LK. So one job is done. Then you have to calculate here force F bar. We have given here only one force is acting downward parallel to the y-axis. So you can convert this force into vector by multiplying the unit vector. So this force is acting along the y-axis but negative direction. So x component will be equal to 0. Y component is F but negative value because it is acting in the opposite direction multiplied by j plus V of 0k. And now you have to carry out the cross product and you have to identify the bending moment about the x-axis, y-axis, z-axis. So we have r bar p cross f bar. You know the method to find out the cross product. For cross product, first you have to write down I, then j, then k. The second row you have to write down the coefficient of position vector which is equal to a, 0, L. Then you have to write down the coefficient of force vector under ijk, that will be 0, minus f and 0. Now find out the value of this determinant and compare with mxi, myj and mzk. So let's solve this. First of all we have I, then we have 0 into 0 is 0, then we have minus f into L, minus f into L. Then second term is always negative, that is minus j, a into 0 is 0, minus 0 into L is 0, plus we have k, then we have a minus f is minus a into f, 0 into 0 is 0. So we'll get this value is equal to minus and minus is plus, so we have f into L times I plus we have 0j minus a into f multiplied by k, where I is a unit vector, j is a unit vector and k is a unit vector. Below this we'll write the standard vector that equal to mxi plus myj plus mzk. Remember, mx is a bending moment about the x-axis, my is a bending moment about the y-axis, and mz is twisting moment, that is a torque. So in this case, if you compare the coefficient, you will get mx will be equal to f into L, and that is a positive value. Because of positive value, we have bending moment about the x-axis is counterclockwise. So this one is reaction at fixed end, that is at O. So directly you have to show this reaction. You have to show the bending moment at point X anticlockwise. Then we have My. The bending moment about Y will be equal to 0. And we have twisting moment is Mz, that is we called as torque. That torque is equal to minus A into F, minus AF. But value is negative, so we can write this value as A into F and will be clockwise. So all these are the reaction at O. So without doing the P-body diagram, using the vector concept, that is Rp cross F bar, we can find out the reaction at point O. So one force will act downward as it is because force we have to shift at point O. Then one bending moment you have to show at point O, which is F into L, is anticlockwise, and one twisting moment you have to show about the Z axis, which is A into F. But this twisting moment you have to show at point O. So all these value of bending moment about X axis, Y axis and Z axis you have to show at point O. So by taking the cross product here, we have obtained the reaction at point O. One reaction you have to show is mx bending moment about the x-axis, that equal to F into L. But you have to show it anticlockwise. So from this side you have to visualize and you have to show the anticlockwise moment about the x-axis. So this one is an anticlockwise bending moment about the x-axis is F into L. At the end Q, we have to show the reaction bending moment. This one is anti-clockwise, so you have to show it clockwise. That will be like this. So this one is a bending moment about the x-axis, that will be equal to FL. Then you have to show here the twisting moment about the point Q and about point O, and we have to show the torque at O and at Q. So this one is a torque acting. In addition to this, the shear force will act at O, which is equal to F, because F is shifted as it is, so its direction is downward and will be shown like this. So on this cross section here, which is a circular cross section, we have to identify the effect of bending moment, effect of the shear stress due to torsion, and the shear stress produced. This shear force is due to bending. To observe the effect of bending moment, we'll visualize from this side. In that case, this point is same as equal to O, this point equal to Q, this axis will be Z axis, and this axis will be to Y axis. And you have to show the bending moment, which one is acting clockwise. Now this time X axis is perpendicular, so we can show the bending moment at this section will be like this. So this one is bending moment about the X axis, that equal to F into L. Opposite reaction will be shown here in an anti-clockwise signs, will be like this. So due to this bending moment, the bar will bend. So the bar will bend somewhat like this. So in this position, the bar will bend. So bottom fiber will become in compression and the top fiber will come in tension. And we know the bending stress distribution, it will be tension on this side and it will be compression on other side. So this one is a compression and this one is tension, tension and compression. And we can calculate the value of bending stress here. First of all, I will show you the distribution is linear. This point is same as equal to O as well as point Q. Both points will be on the neutral axis. So this one itself will be taken as a neutral axis. As far as the torque is considered, torque is uniform over the entire circular cross section. So this one is showing you the variation of shear stress, that is tau, due to torsion, which is torque multiplied by radial position divided by J. And the maximum torque will occur at the outer periphery. So this one is a distribution of a shear stress due to torsion. And one shear force you have to show, which is acting on the circular section. So this one is representing the circular section where we have a transverse shears is acting. So this one is representing the transverse shear V is equal to F. So shear stress distribution will be at neutral axis, will be maximum value, and then the shear stress will go on decreasing. So this one is a shear stress distribution. Average value of the shear stress will be equal to the shear force is V divided by area A, and here this value represents the maximum shear stress, that is at neutral axis. So shear stress at neutral axis in the case of circular section will be 4 by 3 times tau average. So three stresses you have to study for the given loading. One is the bending stress, then we have shear stress, and then we have the shear stress due to the transverse shear force. Now the last part is very important for us. For this one we'll consider the point O and we'll show very small thickness here. So this one is representing our point O. Now we are looking from the Z axis, so this one is our neutral axis equal to NA. Neutral axis here overlap with the X axis, so this one is same as our neutral axis NA. This end is fixed end, so we have taken a very small thickness here. For this purpose we'll consider the two critical points. One critical point we'll consider on the top fiber, that is at point A. So I will show this critical point somewhat with a small thickness. So you are viewing from the front view, so you can visualize this view, and one will take at the neutral axis, that is this section. So this one you are visualizing in the front view. Say this one is the B, where we have to find out the state of stress at A and the state of stress at B. If you observe these points here of a bending stress, so A will be on the top fiber, so this one is A. on the top fiber, B will come on the neutral axis. Then as far as the shear is considered, the shear is at this point is equal to A, and the shear at this point will be equal to B. So this time we have tau A is same as equal to tau B. Since both are on the outer fiber, we have T multiplied by radius capital R divided by J. And this one is the neutral axis in the case of average shear. So this point represents here A, where we have the contribution of the shear stress will be 0, and this point is representing B, where we have on the neutral axis we have shear stress will be equal to the shear stress at neutral axis, which is same as 4 by 3 of tau average, that is 4 by 3 of V by A. We'll make here three-dimensional state of a stress, so I will construct here a cube. So this projection we are giving for three-dimensional, so we will make a cube here of a three-dimensional at B as well as at A. So you have to show this cube, and we'll develop the state of a stress at A as well as B. Now again, to get your concept clear, this will be the state of a stress at A, and this one is representing the state of a stress at B. This one is representing the hatch area that you are visualizing from this side, that is from Z side. Now you are visualizing. So this one is you are facing from Z side. First stress you have to show the bending stress at point A, which one is outward. On this face we have bending stress. So this face will get here bending stress, that will be equal to sigma B, and this value of sigma B is equal to, this is 32 times m by pi d cube. Now as far as the point A is considered, we have to show the shear stress also. For that one we have to see the direction of torque. So in this case the direction of torque at point O will be like this. So this one is the direction of torque. So the shear stress will act in this direction, which one is same as the direction of anti-clockwise. So if you draw the perpendicular here, you will get the direction of shear stress will be anti-clockwise. So on this face I have to show here one shear stress. So this one is a shear stress tau, and this shear stress is due to the torsion. And the shear stress at point B, which one is outer fiber, is a maximum value, is given as T into capital R divided by J. So we have shear stress due to torsion is T into R by J. So one by one you have to complete all the three figure on face A. Already we have shown the bending stress that equal to 32 m by pi d cube. This one is the maximum value of the bending stress on the outer fiber, and the arrow is outward because it is in tension. Then we have shown the shear stress on the outer fiber is maximum, that equal to T into R by J. And next job we have to show the shear stress at point A due to the force F. So this shear force will act in a vertically downward direction, that will be equal to V is same as equal to F. And for this shear stress, if you observe the distribution, then we observe that at point A the shear stress will be equal to 0, but at point B it will be maximum value. So there is no contribution of a shear stress due to the shear force V. So we have a transverse shear at point A will be equal to 0, so that contribution will not show. So you have to show the complementary shear due to torsion here. So this value will be same as equal to tau, and same you have to show on the other side. One arrow of sigma B you have to show on the other side. So this one is a balanced state then. Now focus on point B. So on point B you have to first show the bending stress, but this is at neutral axis. So point B is at neutral axis, so contribution will be 0 due to bending stress. So at neutral axis, that is at B, we have contribution due to bending stress will be equal to 0. So we will not show any bending stress here. Then we have the shear stress due to V you have to show, and one is due to torsion you have to show. Now for torsion again you have to show the same direction, that is the direction is downward. So on this face you have to show one shear stress. This will be the value of tau B due to torsion, and the shear stress due to torsion at point B will be same as equal to T into R divided by J. that is the polar moment of inertia. Remember here the point B is an outer fiber, so it has a maximum possible value. Secondly, you have to show the shear stress at point B, which is on neutral axis. So on B will be the maximum shear stress, that is the tau at a neutral axis. So that value you have to again show it downward. So this value represent here the shear stress at neutral axis will be equal to 4 by 3 of tau average, which is V divided by A. So for B there is no contribution of a bending stress, only the two shear stress will act and they are the same nature, so they can be added. Now the shear stress due to the shear force is negligible as compared to the torsion, so only one stress will act at B. Now there are two stresses acting at point A, one is a bending stress and one is a shear stress. This value will take as sigma x, this value will take as tau xy. We know the sigma max and sigma minimum. Sigma maximum and sigma minimum is given as sigma x plus sigma y by 2 plus minus under root of sigma x minus sigma y by 2 whole thing square plus tau xy square. So the shear stress and the maximum normal stress will be maximum at point A, and therefore the critical state of a stress is represented by A, not at B. So our design is based on the critical state of a stress, that is at point A. So this time the failure will occur on the top fiber, or we can have a failure will occur at the bottom fiber. Now if I show you the bottom fiber, which will again I have to show with this front view, and we have a three-dimensional figure. Now for the point C, which is at the bottom, we have bending stress. So I will just show here the C. So this face is the same face, that is a front view. So bending stress will act here, but in compression in nature, that will be sigma B. Now as far as the direction of the shear stress is considered, I have to show on this face this shear stress. So this will be the value of the shear stress equal to tau at point C, which will be same as equal to T multiplied by R divided by J. And at point C, which is again at bottom, so we have transverse shear at C will be equal to 0. Only two stress will act. So this one is the state of a stress at C. This one is the state of a stress at A. Naturally the state at A and the state at C will be same magnitude wise. But at point B, we have a stresses are less. So either A is the critical state or C is the critical state. That you can analyze by using the Mohr circle. So next our job is to understand the clear concept of Mohr circle, how to find out the principal stresses, the principal plane angle and the plane of maximum shear. So again one more time we visit the Mohr circle and we'll do this thing in detail. This is the best way I try to able to explain you how to develop the state of a stress. For this one, the basic state distribution must be known to you. Bending stress is a linear variation, shear stress is a linear variation, and the shear stress due to shear force is a parabolic distribution. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.